Thank you, Anne. And before I starting, I want to say thank you to Linus and Anne for organizing this workshop. I think I really enjoy this coming together. And as the title said, I'm going to talk about multi-level and Carlo methods, in particular for parametric expectations. I'm going to explain all the components. But the first disclaimer is that while this is a workshop on kind of also computational tools and software, I will not be talking very much about software or implementations. I would rather like to use opportunity to kind of see or explore a little bit how practitioners or people that work more closely with models respond to these type of methods that we have been developing in applied mathematics. And in particular, that's kind of joint work with Fabio Nobile from EPFL in Switzerland and two of his former postdocs and PhD students. Okay. So the setting is very similar to what Niklas described earlier. Namely, for us, we consider we have a certain model, black box, best case scenarios. What could be this wave equation that Niklas described, could be the traffic flow problem from the talk earlier, or even some CO2 capture and storage problems that we've seen yesterday. And of course, there is some random input that goes into our model. Could be a few parameters, could be random functions like this random fields that Niklas had. And then our model, based on this random input, uses a certain output, what I call a quantity of interest, which here's where we have to solve our model. It could be a function like in the traffic flow situation where you have the density, but for the simplicity and for the sake of this talk, I'm going to limit myself to scalar values, so real value quantity of interest. And as the picture already indicates, I'm talking about the forward propagation of uncertainties. And we want to do some multi-level with that. I think later today, we also see a talk about the inverse, so multi-level inversion by Mikkel. But let's stick for the forward propagation here. So let's recall, let's say we have some the input, some density on the input. Our model does something, and we get a certain density on our output. Now, what we then want to do is, well, hey, we would like to understand the quantity of interest, this random quantity of interest, a bit better. And we would like to make as few assumptions as possible to keep it as general as possible. Now, of course, that's an overly simplified model because in practice, there will be some approximation. So we only have oftentimes access to a computational model, like the finite element approximation that Niklas was referring to. So then, of course, also we have an approximated quantity distribution or quantity of interest that we can compute. I just put this H here to indicate some approximation. Okay, and since Niklas already introduced multi-level Monte Carlo method, I can be a bit quicker here. So the most easiest setting is I'm thinking about a level of discretizations. Doesn't have to be discretizations, but let's stick with this thought process here. So I have different levels of discretization at which I can compute an approximate model. And then so I want to compute the expectation, let's say, for our quantity of interest. I approximate it by its approximation on the finest level, L, and I'm using this telescoping sum as you do in multi-level Monte Carlo. And then the benefit I have is I can approximate each expectation in this representation using a different number of samples on the different levels. And why is there any use in that? Well, if I'm looking into the error, for example, a mean squared error of what I can compute using my approximations, then I get this separation in the squared bias term and what I call statistical error. And the observation is that if this variance term here of this fine approximation compared to its coarse approximate counterpart, if this decays, if I'm going further and further to finer levels, then I can get away with fewer and fewer samples on those finer levels. Okay, and that's then the whole idea. I can now try to identify conditions, how to choose my finest level and the number of samples on each level. And this is the usual idea multi-level by balancing all error criteria. We had the same formulas on Niklas' slides already. That's why I'm quite quick here. What then people like to do is they kind of summarize the result from an estimator in a so-called complexity, which balances the accuracy that you obtain versus the computation cost that you have to invest. So under some assumption that you have a certain rate alpha at which your computation model gets more accurate in expectation, so this is the so-called weak a weak rate of convergence or weak error, and a certain rate beta at which the variance gets smaller, and a certain cost gamma at which the obtaining realizations from our computation model get more expensive. The canonical complexity for this multi-level Monte Carlo estimator is this term here. So best case, if the variance decays sufficiently quickly compared to the cost increase, you can get a computational cost up to epsilon to the -2 if epsilon squared is our mean squared error goal, and some other cases. But the important observation is you are always better than Monte Carlo. Okay, of course you can do the same analysis for other criteria, but that's not what we are after today. So this multi-level structure is quite simple, right? So in some sense there's not much going on. You need a bunch of hopefully kind of natural assumption, so you can do some mathematics. But what I want to emphasize here is that I believe when talking about uncertainty quantification, assessing the expectation is a very good starting point, but it should not stop at just assessing the expectation of an uncertain quantity of interest. And my typical example is always that if I have, for example, a bimodal distribution, something like this, and let's say I investigate a kind of a Brownian particle living in a potential which is induced by this distribution, then I would get a time series of this form. And if I'm just looking in, let's say, the time average of such a signal, I would get that the average is around 0, right? The expectation is 0, but this, of course, has very little information about the actual position of my Brownian particle in this potential. Okay, instead, maybe as a first improved way of quantifying uncertainties would be, hey, maybe let's look not only at the mean, at the expected value, but maybe also at the variance. So how much fluctuation there is around the mean value. And this then led us to think about central moments. So we wanted to construct, so think about p equal 2, then this is just the variance, but you can generalize the ideas. So can we construct multi-level Monte Carlo estimators that are tuned such that we can guarantee a certain approximation error, epsilon squared, such that the cost is minimized? And the answer is yes, that is possible. So you can also develop multi-level Monte Carlo approximations for the variance, and then of course for third, fourth, and so on, higher order moments, which then gives you information about the tails, for example, skewness and kurtosis. So that was nice. But then we figured, hey, we are going the direction of quantifying more about the statistical properties of our quantity of interest. And in fact, there are applications like those of risk-adverse optimization, maybe some design optimization that need even further information about the distribution, such as quantiles. So quantiles, or conditional value at risk or value at risk, are objects which receive more attention because they are sometimes related to robustness of a distribution or risk measures. So a typical example would be, we want to find a certain design parameter Z that minimizes a certain risk, when also the risk is something that depends on the distribution of our random quantity of interest, right? And for such an approach, what was quite natural for us, or the approach that we took, is we generalized the picture and we looked into so-called parametric expectations. So we still have our quantity of interest, but now we introduce the function little phi, which now also depends on an additional parameter. And just to give you two examples, one would be if that we can use this representation to look into the characteristic function, which has a lot of information about the entire distribution, but sometimes a bit more natural, maybe for us to look into the cumulative distribution function, so the entire CDF. And since this is a quite nice function, somehow the discontinuity in this indicator function makes our approach makes it much, much harder to estimate. That's why I'm going to focus on this one briefly. So we want to now construct a multi-level Monte Carlo estimator for the CDF. If we do this naively, and even, let's say, if we fix a certain point theta in our domain, then there is still not much gain possibly to use multi-level Monte Carlo, because of the discontinuity, this variance may only decay slowly. And this has been observed previously, and there's a bunch of remedies ranging from kind of some regularization of this indicator function to some moment matching procedures and so on and so forth. And there's a nice review article by Mike Giles to appear in the next proceedings from MCQMC. Okay, our approach is slightly different. So what we are doing is we are making our life more complicated first. So bear with me. So we're defining this function here. Okay, it looks kind of abstract, and please just take it as given. So here we have the positive part, and the reason why we took this function is that now if I'm computing this expectation here, I get some abstract or some function, and it is connected to the CDF in the sense that if I'm computing the derivative of this capital phi, then I just have to rescale this derivative to get directly my CDF. Okay, so there is some information in it, but I have to compute derivatives now. So in some sense, I now want to approximate phi and its derivatives, and then I can get something about the CDF. In fact, I can get even more. By using this function, I could also get an approximation of the PDF, so the probability density function, by computing second derivatives. Optimizing this function gives me the quantile, or even evaluating the function, so the point at which the function is minimized gives me the quantile, and the value attained at the minimizer is the so-called condition valid risk. So this particular choice is extremely convenient to extract lots of information from the distribution. How do we construct now our multi-level Monte Carlo approximator? Well, and we want to do this uniformly on some interval. The idea is very simple. So far we know how to do this pointwise in our theta space. So if theta is fixed, and this is just an expectation, I can do this expectation with my basic multi-level Monte Carlo setting. And now the idea is, let's do this for a bunch of points theta, which I call nodes, and then we interpolate. So I would get a picture like this. I have my multi-level Monte Carlo estimator here, 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 and so on, and I interpolate those points to get my functional approximation to my capital function phi. Interpolation, now you can think of, for example, you could do something in global polynomials, like Chebyshev points, or splines. So there's a bunch of a priori properties on splines that we need for the proofs, and they are well established in numeric analysis. And based on this, then we can also look into an error. So this is our approximation based on the interpolation. That's the mth derivative of our true function, and my mean squared error now is defined as the expected squared error in the L-infinity norm of our set theta. And then you do the usual analysis, you split your terms, and you find, hey, I find 3 terms. First term, I can control the number of interpolation points n I need. I can use a squared bias term to define what my finest level then is. And at the end, I can optimize for the sample size. And you can do most of the analysis by pen and paper. And you get a certain complexity theorem, as we had similar to the expectation that we've seen before. Again, some assumption at which quantifying how fast our method, our computation model gets more accurate, how quickly the second moment, so it's something that's correlated or related to the variance decays, and how quickly the cost increases. Now, if you check carefully, so we're being penalized for a function approximation by a logarithmic term. Okay, that's not too bad, but there's also this term here. However, this can be removed if you're focusing yourself on computational heavy models. So then, in fact, we're only losing a logarithmic term. And this is for splines in particular. And if you do, let's say, Chebyshev polynomials, you need stronger assumptions on our function phi, but you get a similar result. Now, this is for the function, approximating the function itself. We can also do the same then, of course, for a certain number of derivatives we want to compute. And here now, all of a sudden, well, it means all of a sudden, unsurprisingly, in addition to this logarithmic term, we're also losing on the rate, right? Which, at least for splines, we do not lose on the rate that drastically for analytic functions, such we can use spectral conversions in Chebyshev points. Okay. I want to just make one remark that now the entire construction was done to assess the cost to get to the CDF effectively. So first derivative, let's say, m equal 1. But as I teased on earlier, we also would like to have the quantile and the condition value at risk. And because of some nice monotonicity is what you get, that if you, for example, get a uniform error on your cumulative distribution function, you get the other guys, so the quantile and the condition value at risk, by simply post-processing the CDF at no extra cost, right? So the same cost. Okay. There is some practical consideration that had to be done in a recent work to make this practical, and it has then been implemented in a Python library XMC. And I want to briefly showcase one example where we use that to explain a little bit what's going on. So we took a very simple toy problem of Navier-Stokes flow in a cylinder. So we have Stokes problem here, velocity field U and pressure P, and we would like to so we're going to have no slip boundary conditions on top and lower bound. We will have an inflow on the left channel side and an outflow on the right channel side. I'm showing you here already 2 levels of discretization that we used. And what is uncertain in our model here is the profile of our inflow. So here we take some kind of Caron-Loewe type expansion. That's a few realizations of our inflows on the left boundary, and our quantity of interest is so-called track coefficient, which is the first component of this vector. Okay, and then we look into the in this particular example, we're computing the 70% quantile, or more precisely, the 70% conditional value at risk. We're defining in this work, we've developed some adaptive error estimator, which is needed, we developed an a posteriori error estimator, which is needed to develop an adaptive multi-level procedure, right? Because typically you don't know all the rates, you don't know all the constants, alpha, beta, gamma, and the constant in front. So you need adaptivity in the simulation to get to large-scale problems. And then we're using our method, and we see that, hey, we get this is our multi-level Monte Carlo, time to compute our estimator versus tolerance that we require, and we compare this to a Monte Carlo. We see that we are not just a few orders of magnitude faster, but also the slope is better. So if we're going to even finer tolerances, that's precisely the kind of efficiency improvement we would like to get from multi-level techniques in general, and here it worked out quite nicely. So this brings me to the conclusion, since we are already over close to lunch break. What I want to, again, I leave the conclusion for you to read, but what I want to say is I'm really interested to see if people that have more expertise with models and modeling frameworks, if you have an interest in these models, because I think then we have a strong motivation to look into developing these techniques also in the context of your Bridge framework. Thank you for your attention.